The light hitting your eye right now left its source before your species existed. It has been traveling for 2.5 million years through a near-perfect vacuum, crossing a distance so extreme that no unit of measurement your brain was built to process can contain it. In October of 1923, Edwin Hubble placed a single measurement on a photographic plate at the Mount Wilson Observatory in California and proved that the faint smudge you can see with your naked eye on a clear night is not a cloud of gas inside our galaxy. It is an entire separate galaxy, 2.5 million light-years away, containing 1 trillion stars. It is larger than the Milky Way. It is approaching us. And the fastest object humanity has ever launched into space would need 44 billion years to reach it, more than 3 times the current age of the universe. For most of human history, we had no idea it was even there. Then, a single pulsating star on a glass plate changed the size of the known universe overnight. What lies beyond that smudge is a structure so vast it makes our galaxy look like the smaller sibling, and the gap between them is a physical boundary that known physics will not allow biology to cross. Tonight, we will measure that boundary, trace that distance, and sit with what it means to be alive inside a universe built on a scale that was never designed for us. If this is the kind of journey you want to take, subscribing takes 2 seconds and it keeps these videos coming. Are you ready? Let's begin. You think you know how big the Earth is. You have seen the photographs, the pale blue dot suspended in darkness, the curved horizon photographed from orbit, the full disk of the planet hanging in the black. You have probably flown across an ocean, pressed your face against a small oval window somewhere over the Atlantic, and felt, somewhere around hour 6, a creeping and genuine sense that this planet is enormous. That the world stretches in every direction, far beyond anything your legs could cover in a lifetime. And you are right. Measured against a human body, the Earth is staggeringly large. The circumference at the equator runs to roughly 40,075 kilometers. If you wanted to walk that distance at a typical human pace of about 5 kilometers an hour, no stops, no sleep, no rest, it would take you approximately 8,000 hours. That is more than 330 days of continuous walking. Nearly a full year of your life, without a single pause, just to trace the outline of the planet you were born on. Board a commercial aircraft, and the numbers change, but the sense of scale does not vanish, it just shifts. At a typical cruising speed of around 900 kilometers per hour, a non-stop circumnavigation would take roughly 45 hours. Nearly 2 full days in the air to circle the world once. Here is the thing about those numbers. They feel enormous because your brain was never built to process planetary distances. Your intuition for space was calibrated over hundreds of thousands of years by a species that walked. The ancestors who survived long enough to pass their genes forward were the ones who could judge the distance to a watering hole, track a herd across a valley, and navigate home across a landscape measured in tens of kilometers at most. When Homo sapiens began walking out of Africa, roughly 70,000 years ago, the journey to the southernmost tip of South America took approximately 10,000 years of generational migration. 10,000 years to cross a fraction of the planet's surface. The Earth was built on a scale that overwhelmed the biology living on it, and that biology is you. So when a number like 40,000 kilometers hits your ears, your brain reaches for a familiar scale and cannot find one. It files the number away as large and moves on. What it cannot do, what it was never designed to do, is feel the actual distance. This matters, because everything that follows depends on your willingness to accept that when the numbers stop making intuitive sense, that is not a failure of comprehension. That is the numbers doing their job. Hold that thought. Because we are about to zoom out by the first of many levels, and the planet you just spent several minutes contemplating is about to disappear. Start with something you have never visited, but probably believe is genuinely extreme. The Mariana Trench sits in the western Pacific Ocean, and at its deepest point, the Challenger Deep, the ocean floor plunges to approximately 10,984 meters below the surface, nearly 11 kilometers straight down. Getting there requires a purpose-built submersible with a titanium pressure hull capable of withstanding water pressure exceeding 1,000 times what you feel standing at sea level. The temperature hovers just above freezing. It is permanently, absolutely dark. Fewer than 30 people in all of recorded history have ever reached the bottom. In January of 1960, 2 men made the first descent in a vessel called the Trieste. Jacques Picard and Don Walsh took 4 hours and 48 minutes to sink to the floor. They sat on the bottom of the world, separated from instant crushing death by a few centimeters of steel, and looked out through a small porthole at nothing. Total blackness. The pressure outside the hull was enough to collapse a naval submarine. By any human standard, that is an extreme place. Now place it in context. The Earth's diameter is approximately 12,756 kilometers. The Mariana Trench is roughly 11 kilometers deep. If you shrank the Earth to the size of a standard basketball, a ball roughly 24 centimeters across, the Challenger Deep would be a scratch less than 1/4 of a millimeter deep. You could run your fingertips slowly across the entire surface of that basketball, across every ocean floor, every mountain range, every continental shelf, and the deepest point on the planet would feel like nothing at all. The feature that required decades of engineering and a specially built titanium vessel to reach is, at planetary scale, invisible. This is the first pattern the universe is going to show you, and it will not be the last time it shows it. Things that overwhelm human capability often vanish completely the moment you zoom out by a single level. The Mariana Trench is a genuine frontier of exploration. To the planet it sits on, it is a surface imperfection too shallow to notice. Keep this pattern, you are going to need it. The distance between the Earth and the Sun is approximately 150 million kilometers. Astronomers call this distance 1 astronomical unit and use it as the baseline measurement for everything else in the solar system. 1 astronomical unit, a number that appears tidy on paper and is almost meaningless as a human concept. Try to make it physical. At commercial cruising speed, the journey from Earth to the Sun would take over 19 years of continuous flight. A child born the day you took off would be entering adulthood by the time you arrived. At bullet speed, roughly 1,700 kilometers per hour, it would take over 6 years. 6 years at bullet speed, without stopping, just to reach the nearest star. And light itself, traveling at just under 300,000 kilometers per second, takes 8 minutes and 20 seconds to cross that gap. Think about what that actually means. When you look at the sun, when you squint against the glare on a summer afternoon, or watch it touch the horizon in the evening, you are not seeing it as it is right now. You are seeing it as it was 8 minutes and 20 seconds ago. If the sun were to vanish at this exact instant, you would continue to feel its warmth, see its light, and have no knowledge whatsoever of its disappearance for the time it takes to brew a cup of coffee. The sun could be gone, and you would be sitting here, watching 8-minute-old light fall across the floor, entirely unaware. That is how far away our own star is. But the distance is only the beginning of the reckoning. Because the sun itself, once you stop treating it as a lamp in the sky and start measuring it as an object with actual dimensions, is something your intuition is entirely unequipped to process. The sun's diameter is approximately 1,392,000 kilometers. Earth's diameter is roughly 12,700 kilometers. You could line up approximately 109 Earths side by side and just barely stretch them across the face of the sun from edge to edge. Not as a metaphor, as a physical measurement. 109 versions of this planet arranged in a row to span our star's diameter. By volume, the number is more devastating. The sun is so much wider in every direction that approximately 1.3 million Earths could fit inside it. Every continent, every ocean, every city, every living thing on this planet, duplicated 1.3 million times over, and the sun would contain all of it with room remaining. That object contains 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust drifting between orbits makes up the remaining 0.14%. Jupiter, which could swallow more than 1,300 Earths by volume, is a gravitational footnote in the Sun's accounting. Earth does not register at all. What the Sun is doing with all that mass is stranger still. Deep in its core, where pressures exceed 250 billion times the atmospheric pressure at Earth's surface and temperatures reach 15 million degrees Celsius, hydrogen nuclei are being forced together to form helium. The process releases energy, not a little energy. Approximately 4 million tons of the Sun's own mass is converted into pure radiation every single second. Not per year, not per day, per second. 4 million tons, converted, every tick of the clock. That energy takes tens of thousands of years to fight its way from the core through the dense solar interior, and then 8 minutes to reach your skin. The Sun has been sustaining this output for approximately 4.5 billion years and has enough hydrogen remaining to continue for roughly another 5 billion. In cosmic terms, it is middle-aged. Stable. A G-type main sequence star, the classification given to the most common category of stellar object in the galaxy, the ones that burn at a moderate temperature and last long enough for planets to form and for whatever might develop on them to look up. Your Sun is one of those. Unexceptional in every measurable way. The object that has governed every human religion, every agricultural calendar, every definition of morning and evening since the first eyes opened on this planet is, by the standards of the cosmos, ordinary. That ordinariness matters. It will come back to us. But for now, hold the scale. 1.3 million Earths inside the Sun, 4 million tons of mass erased every second, 8 minutes and 20 seconds for light to cover the gap between it and you. And we have not yet left the solar system. Neptune is the outermost of the 8 recognized planets, orbiting the Sun at a distance of approximately 4.5 billion kilometers, roughly 30 times the Earth-Sun distance. A radio signal sent from mission control on Earth to a spacecraft operating near Neptune travels at the speed of light and arrives approximately 4 hours later. If something goes wrong, the team on the ground learns about it 4 hours after the fact. Any response takes another 4 hours to arrive. 8 hours of round-trip communication delay at the absolute speed limit of the universe. There is no such thing as real-time communication across the solar system. Physics will not allow it. In July of 2015, the New Horizons spacecraft completed its flyby of Pluto after a journey of 9 years. Alan Stern's team at the Southwest Research Institute had uploaded the flyby commands hours in advance because the one-way signal travel time between Earth and Pluto at that distance exceeded 4.5 hours. There was no possibility of guidance during the encounter. New Horizons executed its observations entirely alone, stored everything on board, and then spent 15 months slowly transmitting the results home at roughly 1 to 2 kilobits per second. A flyby that lasted hours took more than a year to download. Voyager 1 is further out still. Launched in September of 1977 and still transmitting, it is the most distant human-made object ever built, currently more than 23 billion kilometers from the Sun. Its radio transmitter runs at 23 watts, roughly the output of a dim light bulb. By the time that signal reaches Earth, spreading outward across an ever-expanding sphere of space, the energy arriving at our antennas is approximately 10 billion times weaker than what is needed to power a digital wristwatch. Engineers at the Deep Space Network use cryogenically cooled receivers and hours of signal averaging just to pull intelligible data from the noise. Voyager 1 has crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, and is the first human-made object to enter interstellar space. A genuine achievement. And yet, despite traveling for more than 47 years without stopping, despite covering over 23 billion kilometers, it remains well within the Sun's gravitational domain. The Sun's gravity extends into a region called the Oort cloud, a vast shell of icy bodies that may stretch to somewhere around 100,000 astronomical units from the Sun, potentially 1.5 light-years in radius. Voyager has not left our star's neighborhood. It has barely cleared the driveway. At its current speed, Voyager 1 would require approximately 73,000 years to reach Proxima Centauri, the nearest star to our Sun, if it were heading in that direction, which it is not. 73,000 years to reach the very next star. Here is what the solar system actually looks like when you try to hold it in your mind honestly. Imagine reducing the Sun to the size of a large grapefruit, roughly 10 centimeters across. At that scale, the Earth becomes a ball barely 1 millimeter wide, sitting about 10 meters away. Mars is a slightly smaller ball at around 16 meters. Jupiter, the largest planet, becomes a sphere roughly 1 centimeter wide, hovering just over 50 meters out. Neptune, a ball slightly smaller than Jupiter, sits approximately half a kilometer from the grapefruit. Half a kilometer. And the Sun is something you could hold in your palm. Between the grapefruit and Neptune, at this scale, there is essentially nothing. No objects, no matter, no landmarks. Empty ground in every direction between a small piece of citrus fruit and a handful of nearly invisible specks scattered across a space the size of a modest town. And at this same scale, with the Sun as a grapefruit, the nearest neighboring star would be located approximately 6,400 kilometers away. The distance between London and New York, on a scale where the entire solar system fits inside half a kilometer. 2 grapefruits, 6,400 kilometers of uninterrupted, featureless, perfectly empty nothing between them. This is the space between stars. Not the space between planets, which already stretches every intuition you have. The void between individual suns in our region of the galaxy belongs to a different category of distance entirely. One that makes the solar system itself look like a tight, cluttered neighborhood. And the solar system is not the Milky Way. The Milky Way is not the local group. The local group is not the observable universe. We are just getting started. The solar system you just measured, the grapefruit Sun, the millimeter Earth, Neptune a marble half a kilometer away with nothing between them, is not an isolated object drifting through empty space. It belongs to something. It is embedded in a structure so vastly larger than itself that the entire solar system, including that 6,400 kilometer gap to the nearest star, would vanish inside it like a single grain of sand dropped into the ocean. The structure is called the Milky Way, and before you can feel what that name actually means, you need to forget every image of it you have ever seen. The photographs, the long exposure spirals, the sweeping arms of blue and gold light are taken from outside galaxies like ours, or assembled from data by computers into composite images. You have never seen the Milky Way from the outside. You cannot. You are inside it, roughly halfway out from the center, surrounded by its disk in every direction. When you look up on a clear, dark night and see that pale river of light stretching across the sky, you are not seeing the galaxy from a distance. You are looking sideways through the disk from the inside at the combined glow of billions of stars too distant to resolve individually, blending into a continuous wash of light. That smear across the sky is your home, seen from within. Here is what that home actually is. The Milky Way is a barred spiral galaxy. Seen from above, from a vantage point no human or human instrument has ever occupied, it would appear as a vast pinwheel of stars, gas, and dust, with curved arms spiraling outward from a dense elongated bar of older, redder stars at the center. The disk of the galaxy, where almost all of its visible matter lives, is approximately 100,000 light-years across. To cross it at the speed of light, the fastest that anything in the universe can travel, would take 100,000 years. 100,000 years. The entire span of modern human existence, the whole history of language and fire and agriculture and cities and science, fits comfortably inside a fraction of the time light needs to cross your home galaxy from edge to edge. The disk is not spherical but flat, shaped, in broad terms, like an enormous dinner plate rather than a ball. In the solar neighborhood, this plate is roughly 2,000 light-years thick. light needs 2 millennia to travel from the top surface of the disk to the bottom, at the position where our solar system sits. When the Roman Empire was at its height, a photon departing the upper face of the Milky Way's disk near our location would only now be arriving at the lower face. That is the thickness of the galaxy we live in, at its thinnest. Within that disk, the Milky Way contains somewhere between 200 billion and 400 billion individual stars. The uncertainty in that estimate is not carelessness. It is a consequence of our position. Because we are embedded inside the disk, thick clouds of interstellar dust block our view of the far side of the galaxy. Infrared observations have penetrated the dust further than visible light ever could, but a precise census of every star in the Milky Way remains beyond the reach of current instruments. What we know is that the count is somewhere in that range, and that each of those stars is a sun. Some are incomparably more powerful than ours. Blue supergiants burn with luminosities hundreds of thousands of times greater than the sun's output. Red hypergiants have diameters so enormous that if placed at the center of our solar system, their surfaces would extend beyond the orbit of Jupiter. Others are far dimmer. Red dwarf stars, which make up roughly 70% of all stars in the galaxy, burn so feebly that not a single one is visible to the naked eye from Earth, despite being the most common type of star that exists. Our sun sits in the middle of this range, brighter than most, dimmer than many, unremarkable in almost every measurable way. Its position within the galaxy is equally unspecial. The solar system sits approximately 26,000 light-years from the galactic center, not near the dense, chaotic core, and not at the sparse outer edge, but embedded in a minor structural feature called the Orion Spur, which branches off between two of the galaxy's major spiral arms, the Sagittarius arm and the Perseus arm. In galactic terms, we live in the quiet suburbs, not the noisy downtown, not the remote countryside. The suburbs. Everything in the solar system, the sun, every planet, every moon, every asteroid, every comet, every spacecraft humanity has ever launched, orbits the galactic center at approximately 828,000 kilometers per hour. That is a genuinely staggering speed by any human measure. And yet the sheer scale of the orbit means that one complete circuit takes approximately 230 million years. Astronomers call this a galactic year. The Sun has completed roughly 19 to 20 of these orbits in the 4.5 billion years since the solar system formed. The last time our star occupied this exact position in the Milky Way was approximately 230 million years ago. The Earth at that moment was in the early Triassic period. Pangaea was still largely intact. Dinosaurs were only just beginning to appear. There was no grass anywhere on the planet, no flowers, no birds. The first small, lizard-like creatures that would eventually give rise to the dinosaurs were picking their way across a landscape that would be almost unrecognizable to any eye that evolved later. That is how long a single galactic orbit takes, and the Sun has done it fewer than 20 times. The visible structure of stars, gas, and dust you can see in galaxy photographs is not the whole galaxy, not even close. Surrounding the disk, extending for several 100,000 light-years in every direction, is a vast invisible region called the dark matter halo. It contains no stars, emits no light, and cannot be detected by any telescope ever built, because it does not interact with electromagnetic radiation at all. Its presence is inferred entirely through the gravitational effects it exerts on the visible matter inside it. In the 1970s, an astronomer named Vera Rubin, working with her colleague Kent Ford at the Carnegie Institution in Washington, was mapping the rotation speeds of stars at different distances from the center of nearby galaxies. The expectation, based on the visible matter distribution, was that stars in the outer regions of a galaxy should orbit more slowly than those near the center, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. What Rubin and Ford found was that the rotation speeds stayed roughly constant, or even increased slightly, far out into the galactic disk, where the visible matter had largely run out. The only explanation was that there was matter out there that could not be seen, a vast halo of invisible mass, wrapping the visible galaxy in a gravitational cocoon, holding the outer stars in their orbits as if they were being pulled by something that simply was not there, at least, not in any form that light could reveal. Dark matter halos are now understood to dominate the total mass of every large galaxy. The Milky Way's entire visible disk, every star, every gas cloud, every planet, contributes only a fraction of the galaxy's total mass. The best current estimates place that total at roughly 1 trillion solar masses, the overwhelming majority of it invisible. At the center of all of this, 26,000 light-years from where you are right now, sits something that the visible structure of the galaxy gives almost no clue about. There is a supermassive black hole at the heart of the Milky Way. It carries the name Sagittarius A star, and its mass is approximately 4 million times the mass of our Sun. 4 million solar masses, compressed into a region of space smaller than the distance between the Earth and the Sun. Its mass was not guessed, it was measured. Over several decades, 2 independent groups of astronomers, one led by Andrea Ghez at the University of California, Los Angeles, and one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, tracked the orbits of individual stars in the immediate vicinity of the galactic center. One of those stars, designated S2, completes a full orbit of Sagittarius A star in approximately 16 years, swinging to within only 120 astronomical units at closest approach and reaching a speed of nearly 3% of the speed of light. The orbit is an ellipse, and the shape of an ellipse directly encodes the mass of the object at its focus. The number that fell out of those decades of careful observation was 4 million solar masses. For this work, Ghez and Genzel shared the Nobel Prize in Physics in 2020. 4 million suns, collapsed into a point you could not see, even if you were standing next to it, sitting at the center of a galaxy containing up to 400 billion other suns, wrapped in an invisible halo of matter that outweighs all of it combined. That is where you live. Now measure your place in it. In December of 1901, Guglielmo Marconi transmitted a radio signal across the Atlantic Ocean for the first time. The signal, sent from a station in Cornwall, was received in Newfoundland. It was a moment of genuine significance, the first electromagnetic transmission to cross an ocean, and it marked the beginning of something that has not stopped since. From that point forward, electromagnetic radiation has been leaking from Earth in every direction at the speed of light. Every radio broadcast, every television signal, every radar pulse, every deliberate transmission sent into space, and every accidental one, every frequency humanity has generated since that December morning in 1901 has been expanding outward into the universe in an ever-growing sphere. That sphere has a radius today of approximately 120 light-years. 120 light-years sounds large. After everything you have measured in this video so far, it probably feels large. So let us place it against what you now know the Milky Way to be. The Milky Way is 100,000 light-years across, humanity's entire electromagnetic presence in the universe, every signal ever transmitted, every radio wave, every broadcast, the complete sum of everything we have ever sent into space, extends approximately 120 light-years from Earth. That is roughly 1/10 of 1% of the galaxy's diameter. If you place the Milky Way on a large dining table and let the table represent the full width of the galaxy, humanity's radiosphere would be a small coin, not a large coin, a small one. Sitting somewhere near the middle of the table, invisible at any normal viewing distance, containing within it every word ever spoken on radio, every television image ever broadcast, every deliberate message ever aimed at the stars. The signal degrades as it travels. Electromagnetic power spreads outward in all directions simultaneously, distributing itself across the surface of an ever-expanding sphere. The further it travels, the thinner it becomes, power falling proportionally to the square of the distance. By the time the faint traces of the earliest radio broadcasts reach even the nearest stars, a few light-years away. The signal is so diluted that detecting it would require instruments far beyond the sensitivity of anything humanity has built. To any observer, even at a modest galactic distance, our transmissions are indistinguishable from background noise. Frank Drake, working at the National Radio Astronomy Observatory in Greenbank, West Virginia, in 1961, developed an equation attempting to estimate how many communicating civilizations might exist in the Milky Way at any given time. His equation broke the problem into components: the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, and so on, and multiplied them together. The Drake equation did not produce a confident answer. It was designed to frame the question, to identify what we did and did not know. But one of its variables has become increasingly clear over subsequent decades. The fraction of stars with planets is very high. We now know that planetary systems are the rule in the Milky Way, not the exception, which makes the radiosphere all the more striking. If any civilization exists on the far side of the galaxy, 74,000 light-years from Earth, they have no knowledge that we exist. Our signals will not reach them for another 74,000 years. We are, from where they stand, the future. Not a distant future, an inconceivable one. And from their perspective, if they have been transmitting for roughly as long as we have, we might be looking at a quiet sky in that direction and concluding that nothing is there. Both civilizations, broadcasting into the dark, their signals not yet arrived. Both surrounded by a silence that is not absence, but timing. This is what it means to live in a galaxy 100,000 light-years across. Not that the distances are large in the abstract, but that they impose concrete, measurable consequences on every form of contact possible between anything within them. Distance is not just space. At galactic scale, distance is time, and there is nothing in the universe that changes that. We have established where we are. We have measured the structure we inhabit and our almost imperceptible position within it. What we have not yet addressed is what lies beyond it, and how the discovery of that answer changed the known size of the universe in a single night. In the early decades of the 20th century, the question of what lay beyond the Milky Way was not merely unanswered. For many astronomers, it was not even a meaningful question. The Milky Way, in the prevailing view, was the universe. Everything that existed within it. The spiral shapes visible through telescopes, smeared, ghostly, catalogued as nebulae, were assumed to be clouds of gas and dust within the galaxy, not separate structures beyond it. The idea that the universe might contain other galaxies, each comparable in scale to our own, each containing hundreds of billions of stars, was considered by many to be not just unproven, but almost absurd. The instruments did not yet exist to settle the matter. The question remained open and contentious for decades, accumulating partisans on both sides without either accumulating enough evidence to prevail. The formal confrontation came on the evening of the 26th of April, 1920, at the National Academy of Sciences in Washington. Two astronomers were invited to make the case for their respective positions. Harlow Shapley, working at the Mount Wilson Observatory in the hills above Pasadena, argued that the Milky Way was vast, far larger than previously estimated, and that the spiral nebulae were small, local objects contained within it. Heber Curtis, of the Lick Observatory in California, argued the opposite. The spirals, he maintained, were island universes, entire galaxies comparable to the Milky Way, located at distances so great that their individual stars could not be resolved. The event has since been called the Great Debate, and it settled nothing. Both men made their arguments. Both had real evidence on their side, and real gaps in their reasoning. The audience went home uncertain, and the question remained open. What ended it was not rhetoric. It was a number. The tool that produced that number had been developed years earlier, and by someone who received almost none of the credit for it at the time. Henrietta Swan Leavitt arrived at the Harvard College Observatory in the 1890s as a volunteer, part of a group of women hired by the director Edward Pickering to analyze photographic plates. painstaking, precise work that the professional astronomers of the era largely considered beneath them. Leavitt was assigned to study variable stars in the small Magellanic Cloud, one of the Milky Way's satellite galaxies visible from the southern hemisphere. Variable stars are stars whose brightness changes over time, and Leavitt spent years cataloguing them, recording the pattern of their fluctuations across hundreds of photographic plates. What she found was a relationship. Among a specific class of variable star, the Cepheid variables, which pulsate in brightness with a regular clock-like rhythm, there was a direct and reliable connection between how long the pulsation cycle took and how luminous the star truly was. Slower pulsation meant greater true luminosity. Faster pulsation meant less. The period of the cycle encoded the intrinsic brightness as surely as a label on a package states its weight. This was a measuring rod of extraordinary power. If you could observe a Cepheid variable anywhere in the sky, measure its pulsation period, and determine its true luminosity from that period, you could then compare that true luminosity to how bright the star appeared from Earth. The difference, the gap between how bright it actually was and how bright it looked, could be converted directly into distance, using the well-established mathematics of how light fades with distance. Leavitt had handed astronomers a ruler that worked across the cosmos, applicable anywhere that individual Cepheid variables could be identified. She published her finding in 1912. It would change the known size of the universe within a decade. She would not live to see it. She died in 1921, a year after the Great Debate, before the measurement that resolved everything was made. Edwin Hubble took up that measurement in 1923 at the Mount Wilson Observatory, using the most powerful telescope then in existence. The Hooker telescope, with its 100-inch mirror, had been completed in 1917 and remained the largest operational instrument on Earth for decades. Its light-gathering power was sufficient to do something no previous telescope had managed: resolve individual stars within the Andromeda Nebula. Until that point, Andromeda had appeared in telescopes as a smooth, diffuse glow, a smear of unresolved light with no internal structure visible. The Hooker changed that. On photographic plates exposed over many nights, Hubble began to pick out individual points of light within the nebula. Stars. Separate, distinct, measurable. Among them, he found a Cepheid. He measured its pulsation period. He applied Leavitt's relationship to determine its true luminosity. He compared that to its apparent brightness, as seen from Earth. And he calculated a distance. The number he arrived at was approximately 900,000 light-years. Even that figure, later revised upwards significantly as measurement techniques improved, eventually settling at approximately 2.5 million light-years, placed Andromeda far beyond any estimated boundary of the Milky Way. The Andromeda Nebula was not a cloud of gas within our galaxy. It was a galaxy in its own right. In his observing notebook, next to the variable star he had identified, Hubble crossed out the letters he had initially used to classify it and wrote an exclamation mark. The Great Debate was over. Not because anyone had won the argument, but because the evidence had arrived. The universe, in a single calculation derived from a pulsating star on a glass plate, had become unimaginably larger than almost anyone had dared to propose. There were other galaxies. There were vast numbers of them. The Milky Way was not the universe. It was one among an unknown multitude. That night changed everything that came after. On a clear autumn evening in the Northern Hemisphere, if you know where to look, you can find a faint smudge of light in the constellation Andromeda. You do not need a telescope. You need only a dark sky and a moment of patience. The smudge is subtle, easily overlooked, easily mistaken for a wisp of cloud or an imperfection in your vision. Ancient astronomers catalogued it. Medieval scholars noted it. For nearly the whole of human history, nobody knew what it was. Now you do. What you are looking at, when you hold your gaze on that faint patch of sky, is the combined light of approximately 1 trillion stars. Not 1 billion. 1 trillion. Every photon reaching your eye has been traveling for 2.5 million years. The light departing Andromeda tonight will arrive at a planet in the Milky Way, if any such planet still exists to receive it. In 2.5 million years from now, long after everything we call human civilization has ended or transformed beyond recognition. And the structure that emitted that light is not a modest one. Andromeda's disk spans approximately 220,000 light-years from edge to edge. The Milky Way's disk, which took us some time to establish is already difficult to comprehend, spans roughly 100,000. Andromeda is more than double the diameter of our home galaxy. That ratio translates into a disk area roughly 4 to 5 times greater, not a marginal difference in size, but a categorical one. If you placed both galaxies side by side, the Milky Way would look like the smaller companion, not an equal partner, a sibling that grew up shorter. The stellar populations make this concrete. The Milky Way contains between 200 billion and 400 billion stars. Andromeda contains approximately 1 trillion. Depending on which estimate you accept for our own galaxy's count, Andromeda harbors between 2.5 and 5 times as many stars as the Milky Way. The galaxy you can see with your naked eye on a clear night, the faint smudge that looks like nothing from a suburban pavement, contains more individual suns than the entire galaxy you live in. At the center of Andromeda, as at the center of the Milky Way, sits a supermassive black hole. Ours, Sagittarius A star, carries a mass of approximately 4 million suns. Andromeda's central black hole, designated M31 star, is not comparable. It is not in the same range. Its mass sits at somewhere between 100 and 140 million solar masses, roughly 25 times heavier than our own. The difference in mass between the two black holes is not a matter of degree. It reflects a fundamentally different history. More gas consumed, more satellite galaxies absorbed, more material accumulated at the core over billions of years of gravitational dominance. Around each galaxy, orbiting in ancient elliptical paths that predate the formation of the solar system, are globular clusters, dense, spherical collections of stars, some containing tens of thousands of members, some containing millions, packed into regions only a few dozen to a few hundred light-years across. These are among the oldest structures in any galaxy, relics of the universe's early epochs. The Milky Way has approximately 150 known globular clusters. Andromeda has roughly 450, 3 times as many, each one a city of ancient stars, orbiting a galaxy that has clearly had a richer and more violent history of consuming its neighbors. The evidence for that history is written in Andromeda's halo. A survey led by Rodrigo Ibata at the University of Strasbourg, together with Alan McConaughey and collaborators, spent years mapping the stars surrounding Andromeda's disk in exhaustive detail. The project, called the Pan-Andromeda Archaeological Survey, revealed something extraordinary. Stretching across hundreds of thousands of light-years around Andromeda, in streams and shells and arcs of stars, was the debris of galaxies that Andromeda had already consumed. Smaller galaxies, torn apart by Andromeda's gravity over billions of years, their stars scattered into the halo like the remains of something that no longer exists. The streams are still there, frozen in the halo, an archaeological record of gravitational violence that played out across epochs of cosmic time. Andromeda is not simply a large galaxy sitting quietly in the local group. It is a gravitational predator with a documented history of consuming its neighbors, a central black hole 25 times heavier than our own, a disk more than double our diameter, and a stellar population that dwarfs the Milky Way's by any estimate. And it is heading toward us, not as a metaphor, not as a distant hypothetical. The gap between the Milky Way and Andromeda is closing right now, at this moment, as it has been closing for billions of years and will continue to close for billions more. What that approach means, what it will produce, and how certain we actually are about what happens next is where this story turns. Before we get to the approach, there is a question that needs settling, because the story of what will happen between these two galaxies depends partly on how massive each of them actually is. And the answer to that question turns out to be far less settled than almost any popular account of Andromeda will tell you. Here is the problem. When you look at a galaxy, what you see is its visible component, the stars and the glowing gas that emit and reflect light. That visible component is real, and it is genuinely enormous. But it is not the majority of what the galaxy is. Surrounding every large galaxy, extending far beyond the visible disk in every direction, is a vast and invisible structure called a dark matter halo. It does not emit light. It does not absorb light. It does not reflect light. No telescope ever built, operating at any wavelength, has directly detected it. Its existence is inferred entirely through the gravitational influence it exerts on the matter around it. The story of how we came to understand this goes back to the work Vera Rubin and Kent Ford were doing in the 1970s. Rubin was mapping the rotation speeds of stars at different distances from the centers of nearby spiral galaxies. The expectation, based on standard physics, was straightforward. Just as the outer planets in our solar system orbit the Sun more slowly than the inner ones, stars in the outer regions of a galaxy should orbit more slowly than those near the center, where most of the visible mass is concentrated. That is what gravity predicts, and gravity was not expected to produce surprises. What the data showed was something else entirely. The rotation speeds did not fall off with distance. They stayed roughly constant, or even climbed slightly, far out into the galactic disk, in regions where the visible matter had thinned almost to nothing. The only explanation consistent with the physics was that there was mass out there that the telescopes could not see. A vast invisible structure surrounding the disk, contributing enough gravitational pull to hold the outer stars in their too fast orbits. That unseen structure is the dark matter halo, and it is not a minor addition to a galaxy's mass. In the Milky Way, the visible stars and gas account for only a fraction of the total. The halo dominates. The best current estimates place the Milky Way's total mass, visible matter plus dark matter halo, at roughly 1 to 1.5 trillion solar masses, with the halo contributing the overwhelming share of that figure. Measuring the total mass of a galaxy is consequently much harder than measuring its visible component. You cannot simply count stars. You have to infer the halo's mass through indirect means. The orbital velocities of stars and gas at large radii, the motions of satellite galaxies, the degree to which the galaxy bends the light of background objects through gravitational lensing. Each method carries its own assumptions and uncertainties, and different methods applied to the same galaxy can produce meaningfully different results. For decades, the received picture was clear enough. Andromeda was the bigger galaxy. Its disk was more than twice the diameter of the Milky Way's. Its stellar population was substantially larger, and estimates of its total mass, incorporating the dark matter halo, consistently placed it at somewhere between 1.5 and 2 trillion solar masses, comfortably ahead of the Milky Way's estimated 1 trillion. Andromeda was the dominant partner in the local group. That was the consensus, and it seemed stable. Then the Gaia spacecraft changed the numbers. The European Space Agency launched Gaia in December of 2013. Its mission was to measure the positions and motions of stars across the Milky Way with a precision that had never been approached before, cataloguing nearly 2 billion objects and tracking the tiny angular shifts in their positions as they moved through space. The data it produced transformed galactic astronomy in ways that are still being worked through. Among those working with Gaia's second data release was Laura Watkins at the Space Telescope Science Institute, who applied the new proper motion measurements of globular clusters orbiting the Milky Way's halo to produce a revised estimate of our galaxy's total mass. The result was higher than many previous estimates, approximately 1.5 trillion solar masses. The Milky Way was heavier than it had appeared. Simultaneously, researchers began applying Gaia data to Andromeda. Jean-Baptiste Salomon at the University of Strasbourg, working with Rodrigo Ibata and colleagues, published a study in 2021 that used the motions of Andromeda's satellite galaxies as traces of the gravitational field their host galaxy was generating. The total mass they inferred for Andromeda was approximately 800 billion solar masses. Not 1.5 trillion, not 2 trillion, 800 billion, potentially less than the Milky Way. Here is what that result means if it holds up. Andromeda, the galaxy with more than double our disk diameter, a stellar population several times richer than ours, a central black hole 25 times more massive than Sagittarius A star, and a globular cluster system 3 times larger. That galaxy may actually be lighter than the Milky Way when you account for the full mass, including the halo. The galaxy that looks bigger in every visible category may weigh less than the one that looks smaller. This is not a settled finding. Other studies using different methods and different tracer populations have produced different mass estimates for Andromeda, some placing it significantly higher than 800 billion solar masses. The methodologies involve different assumptions about the shape and extent of the dark matter halo, the orbital histories of the satellite galaxies used as tracers, and the extent to which those satellites are dynamically representative of the halo as a whole. Conflicting results from rigorous studies do not indicate that anyone is wrong in the simple sense. They indicate that the measurement is genuinely difficult and that the uncertainties are real. The honest position, supported by the current state of the literature, is that the Milky Way and Andromeda are probably comparable in total mass. They are likely within a factor of 2 of each other. Which is the heavier of the two remains an open question. And this matters because the mass ratio of the two galaxies affects the dynamics of the eventual interaction, which galaxy's gravity dominates the merger, how the stellar populations are redistributed, and what the end state looks like in detail. There is a deeper point here that is worth sitting with. Andromeda is the most studied galaxy in the universe beyond our own. It is close enough to see with the naked eye. It has been observed continuously for over a century with increasingly powerful instruments. We have resolved its individual stars, mapped its tidal streams, measured its rotation, catalogued its globular clusters, and imaged its central black hole's sphere of influence. And we still cannot agree, within a factor of 2, on how much it weighs. That is not a failure of astronomy. That is an honest measure of how hard this problem is. The majority of the mass in both of these galaxies exists in a form that no instrument can see directly, in a structure whose extent and profile we can only approximate through indirect means. We are weighing something invisible by watching how it tugs on the things we can see. For our nearest giant neighbor, close enough to be observed with the naked eye, studied for a century with the best instruments ever built, we do not know, with confidence, whether it is heavier or lighter than our own galaxy. That uncertainty is not a footnote. It is a statement about the limits of what we currently know, and it sits at the center of any honest account of what lies ahead for both of these galaxies. What lies ahead begins with what we already know is happening. And what is happening is this: Andromeda is moving toward us. The evidence for that has been accumulating for over a century. It begins with a man named Vesto Slipher, working at the Lowell Observatory in Flagstaff, Arizona, in the years 1912 and 1913. Slipher was not trying to prove that the universe contained other galaxies. That debate had not yet reached its peak. He was simply trying to measure the velocities of spiral nebulae by analyzing the light they emitted. The method was spectroscopy, spreading a source of light into its component wavelengths and reading the resulting spectrum like a barcode. If the source is moving toward you, the wavelengths compress slightly, shifting the whole spectrum toward the blue end. If it is moving away, the wavelengths stretch, shifting toward the red. The size of the shift encodes the velocity. When Slipher turned the observatory's 24-inch Clark refractor toward Andromeda and measured its spectrum, what he found was a blue shift. Not a modest one, a substantial one. Andromeda was not receding. It was approaching, and approaching fast. The measurement gave a radial velocity, the component of motion directly along the line of sight between the observatory and Andromeda, of several hundred kilometers per second toward us. Later measurements refined this figure. Modern observations place it at approximately 110 kilometers per second. At that speed, Andromeda covers roughly 400,000 kilometers every hour. The gap between our galaxy and Andromeda shrinks by approximately 3.5 billion kilometers per year, which sounds dramatic until you place it against the full distance. 2.5 million light-years, or roughly 23.5 trillion kilometers. At the current rate of closure, bridging that entire gap would take on the order of 4 to 5 billion years. Slipher's measurement was the first direct evidence that the motion of galaxies was not random, that gravitational attraction could dominate over any local drift, and that two large systems, separated by an almost incomprehensible distance, were nonetheless locked together by their mutual gravity. It was a significant result, and for a time it sat quietly in the literature, somewhat overshadowed by the larger story that Hubble was building, the expanding universe, the recession of distant galaxies. Slipher's blue shift remained the exception to a rule being written around it. The radial velocity was well measured. What resisted measurement for nearly a century was something harder to pin down: the transverse velocity. How fast Andromeda is moving not toward us but sideways, perpendicular to our line of sight. This matters enormously. The radial velocity tells you how fast the gap is closing. It tells you nothing about whether the two galaxies are on a direct collision course or a glancing trajectory. To know whether they will hit head-on, graze each other, or pass at a wide offset, you need both components of motion. The transverse velocity is measured from the angular drift of the galaxy's position across the sky over time, an almost impossibly small shift to detect for an object 2.5 million light-years away. For decades, models of the Milky Way-Andromeda interaction simply assumed the transverse velocity was small or negligible, defaulting to the head-on collision picture because it was the most tractable assumption and because the radial velocity alone made a collision appear inevitable. Gaia changed that. Roland van der Marel at the Space Telescope Science Institute, working with colleagues using data from the European Space Agency's Gaia mission, published a study in 2019 that applied Gaia's precise proper motion measurements to stars and satellite galaxies in the Andromeda system. By tracking the average motion of these objects against the background of distant quasars, objects so far away that they appear essentially stationary, the team extracted a measurement of Andromeda's bulk transverse motion for the first time with genuine statistical weight. Their estimate placed the transverse velocity at approximately 57 kilometers per second, with uncertainties spanning roughly 40 to 70 kilometers per second. 57 kilometers per second sideways. Compare that to the 110 kilometers per second directly toward us, and it is immediately clear this is not negligible. Andromeda is moving at an angle. The sideways component is substantial enough to make the geometry of the first encounter genuinely uncertain. An independent constraint came from Abraham Loeb at Harvard and collaborators, who used the Triangulum galaxy, the third member of the local group, sitting roughly 3 million light-years away, as a dynamical probe. Triangulum has passed close to Andromeda at some point in the past, and its survival as an intact galaxy places an upper limit on how large Andromeda's transverse velocity could have been. If Andromeda were moving sideways too quickly, the gravitational stress during that close pass would have disrupted Triangulum beyond what we observe today. The fact that Triangulum is still there, still coherent, constrains the possibilities from an independent direction. Both lines of evidence converge. The transverse velocity is real, it is not small, and any honest account of what will happen between these two galaxies has to take it seriously. The story most people have heard goes something like this. In approximately 4 billion years, the Milky Way and Andromeda will collide head-on. The two galaxies will merge over several billion more years into a single massive elliptical galaxy. The night sky will transform beyond recognition. And although the event sounds catastrophic, the stars are so widely spaced that almost none of them will actually collide. Most of that is correct, but the head-on impact part has become more complicated in the light of the Gaia measurements, and the complication matters. The picture that emerges from the transverse velocity data is not a clean direct collision on the first pass. It is a glancing encounter. The galaxies are not aimed at each other like billiard balls on a straight course. They are on trajectories that will bring them close enough for their dark matter halos and outer stellar populations to begin interacting gravitationally, but the centers may not merge immediately. Instead, the The galaxies make a first close approach, swing past each other, and then, because they are gravitationally bound, and because the encounter dissipates some of their orbital energy through a process called dynamical friction, they slow down, turn back, and approach again on a tighter, slower second pass. Dynamical friction is worth understanding briefly. When a massive object moves through a medium of other masses, stars, dark matter particles, any gravitationally interactive material, it creates a slight overdensity of that material trailing behind it, drawn in by its own gravity. That trailing concentration exerts a backward pull on the moving object, a form of gravitational drag. In a galaxy merger, both systems move through each other's extended halos and stellar populations, both experiencing this drag continuously. Each close approach dissipates orbital energy. Each subsequent pass is slower and closer. Over multiple orbits, the two systems spiral together. The van der Marel et al. Modeling from 2012 placed the first pericenter, the moment of closest approach on the first pass, at approximately 3.75 billion years from now. Under glancing encounter scenarios, that timing may not shift dramatically. What shifts is the timeline to full coalescence, where earlier models projected a complete merger within perhaps 1 billion years of first contact. Glancing encounter scenarios extend that significantly. Full coalescence under some models could be delayed to 8 to 10 billion years from the present, depending on the precise orbital parameters and the exact mass distributions of both galaxies. T.J. Cox and Abraham Loeb, working together and publishing in 2008, ran one of the most detailed simulations of the full interaction sequence available at the time, following hundreds of thousands of mass elements through the entire event, from first approach through multiple passes to final merger. Their results laid out a sequence of stages and produced probability distributions for where different stars would end up in the final merged system, including, specifically, the Sun. What their simulations and the broader literature agree on without ambiguity is this: the galaxies are gravitationally bound. The radial blue shift is confirmed, has been confirmed for over a century, and is not under dispute. A major gravitational interaction will occur. No model consistent with the current observations produces an outcome in which Andromeda and the Milky Way simply pass each other and drift apart forever. They are falling toward each other, and they will not stop. What remains genuinely open is the choreography. Whether the first encounter is a near-direct impact or a significant glancing blow. How many passes the galaxies complete before coalescing. How long the full process takes. These questions depend on measurements still being refined and on mass estimates that carry their own real uncertainties. The physics is well understood in principle. The initial conditions are still being nailed down. What we can say with confidence is that something on a scale difficult to fully articulate is coming, that it has been coming for billions of years already, and that the event, when it unfolds, will be unlike anything the word collision is normally used to describe. Here is the image most people carry when they hear the words galactic collision. Two vast structures of stars rushing toward each other. A catastrophic impact. Fire, destruction, solar systems shredded, planets flung into the void. The word collision summons all of that. It is the wrong image entirely. The reason it is wrong comes back to something this video established at the very beginning and has returned to at every scale since. Space is almost entirely empty, not partially empty, not mostly empty. The emptiness is so extreme, so structurally fundamental to how matter is distributed in the universe, that two entire galaxies can pass through each other and their individual stars will almost certainly never touch. Think about what you now know about the space between stars. In the solar neighborhood, the average distance between neighboring stars is roughly 4 to 5 light years. Each star is perhaps 1 million or so kilometers across, a sun-sized object. The gap between stars is measured in trillions of kilometers. If you shrank the sun to the size of a bowling ball and placed it somewhere in a large cathedral, the nearest neighboring star, reduced to the same scale, would be another bowling ball sitting in a different cathedral, hundreds of kilometers away. Not in the next room, not across the street, hundreds of kilometers. Now imagine two such cathedrals passing through each other. Not crashing, passing. The cathedrals interpenetrate, one moving through the other, occupying the same space at the same time. What happens to the bowling balls inside them? Almost nothing. The probability of any two bowling balls from different cathedrals actually meeting in that passage is effectively zero. The buildings pass through each other, and the objects inside them continue almost undisturbed, because the objects are vanishingly small relative to the space the buildings contain. That is a galactic merger. The stars in the Milky Way and the stars in Andromeda are so small relative to the distances separating them that the two galaxies can interpenetrate completely without their stars colliding. Statistically, across a merger involving hundreds of billions to a trillion stars on each side, direct stellar impacts are expected to be extraordinarily rare, perhaps a handful across the entire event. The stars pass through each other's galaxy like two swarms of fireflies occupying the same field, each individual firefly too small and the field too large for any two of them from different swarms to collide. What does happen is something else, something that operates at a completely different scale and is, in its own way, far more dramatic than the impact most people imagine. Gravity does not require contact. It reaches across space, and in a galaxy merger, it reaches across tens of thousands of light years simultaneously. As the two galaxies approach and interpenetrate, the tidal forces generated by their mutual gravity begin to distort both structures profoundly. The outer regions of each galaxy, less tightly bound to their own center, respond most dramatically. Spiral arms are stretched and pulled into long, sweeping streams of stars that arc away from the main body of each galaxy. Stars on the side of a galaxy closest to the passing intruder feel a stronger gravitational pull than stars on the far side, and that differential, the tidal force, progressively warps the shape of the whole structure. Some stars are flung outward onto long, looping trajectories that carry them far into intergalactic space. Others are dragged deep into the combined central region as the cores of the two galaxies spiral toward each other. The elegant, ordered spiral structure that took billions of years to build, the sweeping arms, the rotating disk, the coherent pinwheel shape visible in photographs of spiral galaxies like our own, is dismantled. Not quickly, not in a single event, but progressively, irreversibly, across hundreds of millions of years of gravitational interaction. The gas within the galaxies behaves completely differently from the stars. Stars are compact, discrete objects, widely separated points in an otherwise empty galaxy. Gas is diffuse, extended, spread across enormous regions of space in clouds and filaments. When the gas from two galaxies meets during an interpenetration, it does what dispersed matter does when it collides. It compresses. The compression heats the gas, raises its density, and in the regions where conditions become right, triggers the collapse of material into new stars. The result is a starburst, a period of dramatically accelerated star formation, orders of magnitude more intense than the normal background rate. Regions of both galaxies that had been quiet for billions of years suddenly ignite. The merger blazes with the light of newly born massive stars, radiating intensely in ultraviolet and infrared wavelengths. It is the most visually spectacular phase of the event. We do not have to model this from first principles alone. We can observe it directly in other galaxy systems at various stages of exactly this process. Roughly 45 million light-years from Earth, in the constellation Corvus, two spiral galaxies designated NGC 4038 and NGC 4039, known collectively as the antennae galaxies, are currently in the middle of an active merger. Their overlap region is blazing with triggered star formation. Long tidal tails of stripped stars arc away from both galaxies, extending hundreds of thousands of light-years into the surrounding space. The antennae are a present tense example of what the Milky Way and Andromeda will be doing at some point after first contact. At an earlier interaction stage, the mice galaxies, a pair designated NGC 4676, show two spirals that have made a first close pass and are now drawing apart, trailing the long, narrow tidal tails that give them their name. And the Cartwheel Galaxy, sitting roughly 500 million light-years away, shows the aftermath of something rarer, a smaller galaxy that passed almost directly through the center of a larger spiral, driving a shockwave of compression outward through the disk and producing a ring of intense star formation radiating away from the point of penetration, like a ripple expanding across the surface of still water. These are not simulations. They are real galaxies, observed at different points in a process that we understand well enough to read like a sequence. The starburst phase does not last. The cold gas that fuels it is consumed relatively quickly in cosmic terms, a few 100 million years. The most massive of the newly formed stars burn through their fuel rapidly and explode as supernovae, driving hot gas out of the starburst regions. The supply runs low. The intensity fades. What remains is a merged system growing quieter, its star formation rate declining as the available fuel is exhausted or expelled, beginning the long process of settling into something new. What it settles into is something almost nothing like either of its parents. The Milky Way and Andromeda are both spiral galaxies. They have rotating disks, sweeping arms wound with gas and young stars, an organized plane of rotation built over billions of years of accumulated angular momentum. The structure you see in photographs of spiral galaxies, the elegant pinwheel, the luminous core fading outward into curving arms, is the product of enormous timescales of ordered gravitational evolution. It is, in a sense, the mature and settled form of a galaxy that has had time to organize itself. The merger erases that entirely. What emerges from the multi-billion-year process of tidal distortion, repeated close approaches, starburst activity, and eventual coalescence is a galaxy of a fundamentally different type, an elliptical galaxy, no disk, no spiral arms, no coherent rotation in a single plane. Instead, a roughly spherical or elongated distribution of stars, each following its own orbital path around the combined center, the directions of those orbits scrambled by the gravitational chaos of the merger into something much closer to random. The elegant structure of two spiral galaxies replaced by a smooth, featureless ball of stars. Astronomers have given this future object an informal name, Milkomeda, sometimes Milk-Dromeda. The name is playful, but what it describes is real. The endpoint of the gravitational interaction that is already locked in, already unfolding in slow motion across the billions of years separating us from the moment the two galactic cores finally merge into one. The combined stellar population of Milkomeda is estimated at somewhere between 1.2 and 2 trillion stars. The range is wide because a significant fraction of both galaxies' stars will be flung into intergalactic space during the repeated close encounters before final coalescence, stripped away by tidal forces and scattered into the surrounding void, no longer gravitationally bound to either galaxy. How many stars survive within the merged structure and how many are ejected depends on the precise geometry of the encounter, which remains uncertain. Even at the lower end of the estimate, Milkomeda will be among the larger elliptical galaxies in the local group. By the standards of the enormous ellipticals found at the centers of rich galaxy clusters elsewhere in the universe, it will be unremarkable. The combined center will contain something that no single galaxy in the local group currently possesses in equivalent form. Sagittarius A star, the Milky Way's central black hole, contains roughly 4 million solar masses. M31 star, Andromeda's central black hole, contains somewhere between 100 and 140 million solar masses. When the two galactic cores eventually merge, these two objects will find themselves in an increasingly close orbit around each other, drawn together over billions of years by the same dynamical friction mechanism that progressively saps orbital energy from passing stars. Their eventual merger will not be a collision in any ordinary sense. It will be a coalescence of space-time distortions, and it will release a burst of gravitational waves of a frequency and amplitude that would be detectable across enormous distances. The LISA mission, a joint endeavor between ESA and NASA, designed to be placed in a solar orbit trailing the Earth and using laser interferometry across arm lengths of millions of kilometers, is specifically designed to detect precisely this kind of signal. Low-frequency gravitational waves from merging supermassive black holes are among its primary science targets. The merger of Sagittarius A star and M31 star will be among the most powerful such events in the local group's future, and any sufficiently advanced detector in existence at the time would not miss it. The fate of the solar system within all of this is, on reflection, surprisingly benign. The Cox and Loeb N-body simulations, which tracked millions of test particles representing the positions of stars across both galaxies through the full merger sequence, found that the solar system faces a roughly 12% probability of ending up in the inner regions of the merged galaxy, drawn deeper toward the combined core. There is a roughly 48% probability of ending up at a greater distance from the center than the Sun currently occupies. And there is a small but real probability of ejection into the intergalactic halo, cut loose from the merged galaxy entirely and sent into the surrounding void. What is essentially zero is the probability of destruction through direct encounter with another star. The emptiness protects us even through this. If you were watching from the surface of a planet orbiting a sun-like star somewhere in the merged Milky the changes on any human-relevant timescale would be imperceptible. The stars move slowly enough that no individual human lifetime would register the transformation. But across millions of years, the night sky would become profoundly alien. Stars from Andromeda's population would have become part of your sky's ordinary fabric. The familiar band of the Milky Way, the edge-on view of our own galactic disk, would have warped, brightened in some directions, faded in others, losing its clean arc as the disk's structure was disrupted. New star-forming regions, ignited by the merger's compression of gas, would illuminate portions of sky that were previously dark. The constellations we use to navigate the sky today would have dissolved completely into arrangements of stars that no culture anywhere had ever mapped or named. There is one complication in this picture that should not be quietly passed over. The Sun is approximately 4.6 billion years old. In roughly another 5 billion years, it will exhaust the hydrogen fuel in its core, begin fusing hydrogen in a shell around that core, and expand into a red giant, swelling to many times its current diameter, engulfing the inner planets, rendering Earth uninhabitable if it has not been already. Under the slower glancing encounter models for the Milky Way-Andromeda merger, the final coalescence into a stable elliptical may not be complete until 8 to 10 billion years from now, which means the solar system as a habitable environment may cease to exist before Milky has finished forming. The entity described as our cosmic future may outlast us by billions of years. Milky will not exist in isolation. Both the Milky Way and Andromeda are the dominant members of something larger, a family of galaxies that have been gravitationally associated with one another for as long as the universe has been old enough to contain them. The local group, more than 80 individual galaxies, spread across a region roughly 10 million light-years in diameter, held together by their mutual gravity against the general expansion pulling everything else apart. In mass, in stellar content, in sheer gravitational authority, the Milky Way and Andromeda together account for the overwhelming majority of what the local group contains. Everything else, every other named galaxy in the catalogue of local group members, is subordinate to one or both of them. The third largest member is the Triangulum Galaxy, designated Messier 33. It contains roughly 40 billion stars, less than a quarter of the Milky Way's estimated count. It sits approximately 3 million light-years away, possibly gravitationally bound to Andromeda as a satellite. Its long-term trajectory suggesting it may be drawn into the eventual merger between the two major galaxies, its stars incorporated into Milky, along with those of its larger neighbors. Beyond Messier 33, the members of the local group drop steeply in size and mass, small irregular galaxies, compact dwarf spheroidals, stellar systems so sparse that they barely qualify as galaxies by some definitions. The Milky Way keeps its own satellites close. The Large Magellanic Cloud and the Small Magellanic Cloud, visible to the naked eye from the southern hemisphere as detached, luminous patches of sky distinct from the main galactic band, sit at approximately 160,000 and 200,000 light-years respectively. Both are being progressively disrupted by the Milky Way's gravity, their outer regions pulled into streams that trace their orbital paths across a wide arc of sky. M32, one of Andromeda's closest companions, tells a different story. It is thought to be the stripped remnant of what was once a medium-sized spiral galaxy, its outer disk and arms torn away over billions of years of close orbital interaction with Andromeda, leaving only a dense, compact core. Even this family, the local group, sits within something larger still. In 2014, R. Brent Tully at the University of Hawaii, working with Hélène Courtois at the University of Lyon, and colleagues, published a map of cosmic structure built not from the positions of galaxies, but from their motions. Every galaxy moves through space on two components simultaneously: the general recession, driven by the expansion of the universe, and a peculiar velocity, a motion driven by local gravitational influences, the push and pull of nearby mass. By mapping the peculiar velocities of thousands of galaxies in extraordinary detail, Tully and Courtois were able to trace the boundaries of gravitational basins, regions of space in which all the peculiar velocities pointed, at some level, in the same inward direction. The result was a map of the supercluster in which the Milky Way resides. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans approximately 500 million light-years. It contains roughly 100,000 individual galaxies, including the vast Virgo cluster, the gravitational heart of the local cosmic web, and hundreds of smaller galaxy groups, of which our own local group is one. The local group sits near Laniakea's outer edge, in a relatively underdense region, its peculiar velocity pointing loosely inward toward the supercluster's gravitational center of mass. That center of mass is known as the Great Attractor, a gravitational anomaly whose existence was inferred long before it was understood, because the Milky Way sits almost exactly in the plane of its own galactic disk when looking in the Great Attractor's direction, and the dust and gas of that disk blocked the view for decades. What lay behind it remained mysterious. Now, the broad picture is understood. The gravitational concentration responsible is primarily associated with the Shapley supercluster, an enormous overdensity of matter sitting approximately 650 million light-years away in the direction of the Centaurus and Hydra constellations, pulling the Milky Way and hundreds of thousands of neighboring galaxies toward it at roughly 600 kilometers per second. You are on a planet orbiting a star at the edge of a galaxy being drawn toward a supercluster at 600 kilometers per second, while that supercluster is itself embedded in the web of large-scale structure that makes up the observable universe. And the galaxy, merging with yours, will bring its satellites and its gravitational context with it, consolidating the local group's mass into a single structure that will then face this larger cosmic environment together. Each scale you have visited in this video has made the previous one vanish. Earth becomes a point within the solar system. The solar system becomes invisible within the Milky Way. The Milky Way is a single member of a local group that is itself a peripheral member of a supercluster 500 million light-years across. At every step, the structure that felt enormous a moment earlier simply disappears into what surrounds it. The hierarchy is not finished. There is a layer of this story that goes beyond mere size, beyond the question of how large the universe is relative to us, or how small we are relative to it. It concerns what the universe is doing, actively, right now, at every moment, and what it means for everything you could ever hope to reach or observe or know. Edwin Hubble announced it to the world in 1929, though the evidence had been accumulating for years before his paper made the conclusion unavoidable. Galaxies beyond the local group are not stationary. They are not moving toward us. They are receding, moving away, and the speed of that recession is proportional to their distance. The farther a galaxy is, the faster it is retreating. Hubble interpreted this correctly as evidence that the universe itself is expanding. Not that galaxies are moving through static space like shrapnel from an explosion, but that the space between them is stretching, carrying galaxies along with it the way dots painted on the surface of an inflating balloon move apart from one another as the balloon grows. Not because the dots are moving across the surface, but because the surface itself is getting larger. The rate of that expansion is described by a number known as the Hubble constant, the speed of recession per unit of distance. Its precise value has been the subject of significant ongoing debate, with different measurement techniques producing results in tension with one another. But the expansion itself is not in question. It is among the most thoroughly confirmed facts in all of observational astronomy. For decades after Hubble's announcement, the prevailing assumption was that the expansion was slowing down. Gravity, acting on all the matter in the universe, should be applying a brake. The question was whether the brake was sufficient to eventually halt the expansion and reverse it, or whether the universe would expand forever at a diminishing rate. Neither option fully prepared anyone for what two independent research teams discovered in 1998. The High Z Supernova Search Team, led by Brian Schmidt at the Australian National University, with Adam Rees at Johns Hopkins University among its key contributors, and the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, were both using a specific class of stellar explosion as a cosmic measuring tool. Type 1a supernova. The thermonuclear destruction of a white dwarf star that has accumulated too much mass, detonate with a peak brightness that can be calibrated precisely enough to serve as a standard candle across billions of light years. Measure how bright the explosion appears from Earth, compare it to how bright it actually is, and you can calculate the distance to that explosion with a reliability no other method at those scales could match. Both teams found the same thing. The most distant Type 1a supernovae were dimmer than the expansion rate suggested they should be, not by measurement error, not by a small discrepancy that could be attributed to dust or calibration uncertainty. Systematically dimmer across enough events and enough independent checks to rule out instrumental explanation. The supernovae were farther away than the models predicted. The expansion, rather than slowing under gravity's influence, was speeding up. The universe is not coasting, it is accelerating. The mechanism responsible has been named dark energy. What dark energy actually is remains genuinely unknown. Whether it is a property intrinsic to space itself, a quantum vacuum energy, something described by Einstein's cosmological constant, or something requiring entirely new physics. According to the Planck 2018 cosmological parameter results, dark energy accounts for approximately 68% of the total energy content of the universe. Ordinary matter, everything you can see, touch, or detect, accounts for roughly 5%. Dark matter, which interacts gravitationally but not electromagnetically, accounts for the remaining 27%. The majority of the universe is made of something we cannot identify. What acceleration means, in practical terms, is not merely that distant galaxies are moving away. It means they are moving away faster over time, and that this process has a horizon built into it. There is a distance, currently sitting at approximately 16 billion light-years, beyond which galaxies are already receding faster than light can travel through the expanding space between them and us. Light from those galaxies is, right now, losing ground, moving toward us but being carried backward by expansion faster than it can advance. It will never arrive. Those galaxies are not merely distant, they are already permanently unreachable, and their light is already permanently unable to reach us. The cosmological event horizon is not a wall. It is a geometric consequence of accelerating space, and it is the boundary of everything that will ever be observable from our position, no matter how long we wait or how powerful our instruments become. The astronomer Abraham Loeb at Harvard University calculated in 2002 what accelerating expansion implies across the full sweep of cosmic time. The conclusion is quietly devastating. In approximately 150 billion years, roughly 10 times the current age of the universe, the accelerating expansion will have carried every galaxy cluster beyond our local group across that event horizon. Every galaxy outside the gravitationally bound family to which the Milky Way and Andromeda belong will have vanished from any possible observation. Their light, stretched by expansion toward infinitely long wavelengths, will have faded beyond any conceivable detection. The local group, by then consolidated into the merged elliptical Milkomeda and its satellites, will appear to any observer within it as the entirety of the universe. There will be no receding galaxies to observe, no redshift to measure, no Hubble constant to calculate, no way to infer that space is expanding at all, because the galaxies whose motion would reveal that expansion will be gone. The cosmic microwave background, the faint thermal afterglow of the Big Bang that fills the sky at microwave frequencies, already sitting at a temperature just 2.7 Kelvin above absolute zero, will have cooled further toward complete undetectability, its wavelengths stretched beyond any physical receiver's ability to register them. Any intelligence arising in that future universe will have no observational path to the Big Bang, no evidence of cosmic expansion, no way to discover that any galaxy other than their own ever existed. The universe will look to them like an island of stars surrounded by an eternal, uniform darkness, static, bounded, complete. The picture we would draw of a pre-Copernican cosmos, ourselves at the center of everything there is. And they would be, by every measurement available to them, correct. The cosmological knowledge we possess today, the expansion rate, the age of the universe, the large-scale structure, the microwave background, the abundance of galaxy clusters stretching across billions of light-years, is not permanent. It is a window that opened at a particular moment in cosmic history, after the universe had cooled enough for atoms and stars and galaxies to form, but before the accelerating expansion had swept the evidence beyond reach. We exist in that window. We have been fortunate enough to be here while it is open, and it is, on timescales that dwarf anything human civilization has yet existed for, slowly closing. The universe is not merely large, it is becoming less knowable by the hour. All of this, the expansion, the acceleration, the receding horizon, the vanishing evidence, applies to what lies beyond the local group. It tells you what you will lose access to across cosmological time. But before that reckoning fully lands, there is still the question of what is actually out there, right now, inside the region of the universe that light has had time to cross since the beginning. The observable universe is not the universe. It is a sphere of knowability centered on wherever you happen to be standing. In our case, a rocky planet in the Orion spur of the Milky Way. Its boundary is not a wall or a physical edge. There is no barrier, no membrane, no surface where matter stops and emptiness begins. The boundary is defined purely by time. Light travels at a fixed speed. The universe has existed for a finite duration, approximately 13.8 billion years. The observable universe is simply the region from which light has had sufficient time to travel to us since the Big Bang. Beyond that sphere, there may be more space, more galaxies, more matter. Almost certainly there is. But the light from those regions has not yet arrived. We cannot see it. We cannot detect it. We have no information about it whatsoever. The naive calculation gives an observable radius of 13.8 billion light-years. The distance light could travel in 13.8 billion years at the speed of light. The actual figure is nearly 3.5 times larger. The observable universe has a radius of approximately 46 billion light-years. The reason for the discrepancy is the same expansion that sent the galaxy clusters racing away in Hubble's data. The space through which those ancient photons have been traveling has itself been expanding throughout their journey. A photon emitted from a region of space that was once very close to us has been traveling through stretching space for billions of years, and the source of that photon is now tens of billions of light-years from where it was when the photon departed. The Planck 2018 cosmological parameters provide the precise framework within which this figure is calculated. Within that sphere, roughly 46 billion light-years in radius, how many galaxies are there? The number that circulated for decades was approximately 200 billion. It was an estimate built on the galaxy counts from early deep-field observations, extrapolated across the full sky. Then, in 2016, Christopher Consolis at the University of Nottingham and collaborators went further. Using data from the Hubble Space Telescope's deep field campaigns, combined with mathematical modeling of galaxies too small and too faint for any current instrument to directly detect, they revised the total upward by a factor of 10. Their figure, approximately 2 trillion galaxies within the observable universe. The overwhelming majority of them are dwarf galaxies, small, dim, compact structures far below the detection threshold of existing telescopes. The large spirals and giant ellipticals that dominate the images are, numerically, a minority. 2 trillion galaxies. And Andromeda, at 2.5 million light-years, sits at approximately 0.005% of the observable universe's radius. The nearest galaxy of comparable size to our own, the object we spent much of this video examining in detail, whose merger with the Milky Way is a defining event in our cosmic future, is, by any cosmological measure of distance, immediately beside us. A rounding error from the center of the observable sphere, effectively adjacent. 2.5 million light-years, which we established earlier, no spacecraft humanity has ever built, could cross in under 3 billion years, is, from the perspective of the observable universe's full extent, nothing at all. Now consider what the observable universe itself might be relative to the full universe. In the first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion known as cosmic inflation. The theory was first proposed by Alan Guth at MIT in 1980 and developed in subsequent years by Andre Linde at Stanford University and others. In an almost inconceivably brief interval, measured in fractions of a second, with far more decimal places than most numbers we deal with have digits, the universe expanded by a factor of at least 10 to the power of 26, possibly far more. Regions of space that were once in causal contact with one another were driven apart far faster than light could bridge them. The consequence is that the total universe, the full extent of space that exists, is almost certainly vastly larger than the observable bubble we inhabit. How much larger is genuinely unknown. It may be hundreds of orders of magnitude larger. It may, in the most expansive inflationary models, be effectively infinite. The observable universe is not the universe. It is the tiny sphere of it from which signals have had time to arrive. We are observing a local patch of something whose full extent we cannot measure, cannot reach, and may not even be able to meaningfully define. Step back from that for a moment and consider the full arc of what this video has covered. You began on the surface of a planet whose entire circumference can be circled in roughly 17 hours on a commercial aircraft. You moved outward to a solar system so empty that a scale model with a grapefruit for a sun would place the nearest neighboring star 6,400 kilometers away. You moved outward to a galaxy 100,000 light-years across, containing between 200 and 400 billion stars, whose diameter light takes 100,000 years to cross. You moved outward to a local group spanning 10 million light-years, dominated by 2 galaxies on a converging trajectory billions of years in the making. You moved outward to a supercluster 500 million light-years across, itself embedded in the filamentary large-scale structure of the observable universe. And now you are standing at the edge of an observable sphere 46 billion light-years in radius, containing 2 trillion galaxies, which is itself, almost certainly, a vanishingly small fraction of everything that exists. At every step, the structure that felt enormous, the step before, dissolved into the scale of what came next. Earth is a point within the solar system. The solar system is a point within the Milky Way. The Milky Way is a point within the local group. The local group is a point within Laniakea. Laniakea is a point within the observable universe. The observable universe is very possibly a point within the full universe. The hierarchy does not have a visible top, and the further up it you look, the smaller you become. Before this video turns to what all of this means, it is worth pausing on the most immediate consequence of the scale you now understand. Not the philosophical weight of it, not the existential dimension, but the simple, concrete, physical question that the scale of the universe raises for any species that has ever looked up and wanted to go. The question of how far we could actually travel. Voyager 1 is the most distant human-made object in existence. Launched by NASA in 1977, accelerated by a gravitational slingshot around Jupiter in 1979, it is now in interstellar space, beyond the heliopause, the boundary where the solar wind gives way to the interstellar medium. Its outbound speed is approximately 61,500 kilometers per hour. That figure is not the product of an engine running continuously for 47 years. It is the product of a single gravitational maneuver performed in 1979, after which Voyager 1 has been coasting in free space. No thrust, no fuel expenditure, no propulsion of any kind. It has been falling forward through space on the trajectory Jupiter's gravity gave it, and will continue doing so indefinitely. At 61,500 kilometers per hour, the travel time from Earth to the Andromeda Galaxy is approximately 44 billion years, more than 3 times the current age of the universe. Voyager 1 could have departed at the moment of the Big Bang and would still be less than a third of the way there. The Parker Solar Probe, launched by NASA in 2018, achieves far higher speeds by doing something different. Rather than heading outward, it repeatedly dives inward, falling toward the Sun, accelerating in its gravitational well, and sweeping past at perihelion at approximately 690,000 kilometers per hour. It is the fastest human-made object on record, 11 times faster than Voyager 1. At that speed, the travel time to Andromeda is approximately 3.9 billion years, roughly the current age of the Earth. The fastest object humanity has ever built, traveling at the highest speed we have ever achieved for any physical object, would take longer than the Earth has existed to reach the nearest large galaxy. These are not edge cases. They are not limited by our current level of technology. They are demonstrations of what happens when you try to move through a universe built at the scale this video has been describing. The most credible near-term proposal for dramatically higher velocities is the Breakthrough Starshot Initiative, announced in 2016 and backed by the physicist and investor Yuri Milner, with the theoretical physicist Stephen Hawking among its early advisors. The concept involves using a ground-based array of lasers, delivering enormous combined power to accelerate a gram-scale light sail, a reflective sheet of material with the mass of a postage stamp, to approximately 20% of the speed of light. The design target is a 20-year transit to Proxima Centauri, 4.2 light-years away. The engineering challenges are formidable and unresolved, but the physics is not in violation of any known principle. Apply that same speed to Andromeda. At 20% of the speed of light, the travel time is 12.5 million years. Now consider 10% of the speed of light, roughly 107 million kilometers per hour, approximately 1,700 times faster than the Parker Solar Probe. A velocity achievable by no known or credibly proposed propulsion system for any object of meaningful mass. The travel time to Andromeda, 25 million years. For context, 25 million years ago, the ancestors of the great apes had not yet diverged from the ancestors of the old world monkeys. The line that would eventually produce every chimpanzee, gorilla, orangutan, and human on Earth was not yet a distinct lineage. Einstein's special theory of relativity offers a partial reprieve. Moving clocks run slow. A spacecraft at very high velocity relative to a stationary frame experiences time at a compressed rate, time dilation, confirmed experimentally to extraordinary precision, including by atomic clocks flown on aircraft and by the corrections built into every GPS satellite in orbit. At 99% of the speed of light, a crew would experience subjective time passing far more slowly than observers at rest. Under constant 1g acceleration, providing Earth-like artificial gravity throughout the journey, the subjective travel time to Andromeda compresses to approximately 28 years, a human lifetime. A crew could, in principle, experience the journey within a normal lifespan. The catch is the energy. Accelerating 1 kilogram of mass to 99% of the speed of light requires approximately 4 times 10 to the power of 16 joules. A crewed spacecraft of any practically useful mass, crew, life support, fuel, structure, scientific instruments, would run to, at minimum, several thousand tons. The energy required to accelerate that mass to near light speed and then decelerate it at the destination would exceed the total energy output of the Sun across billions of years of normal fusion. There is no conceivable power source, no theoretical technology operating within known physics capable of supplying it. The physics of time dilation permits the journey in one sense. The physics of energy forbids it in every other. There is a concept that appears whenever the conversation about interstellar and intergalactic travel reaches this point. A way of sidestep the energy problem, the time dilation problem, and the human lifespan problem simultaneously. It is called the generation ship, a vessel so large and so self-sustaining that the crew who depart are not expected to arrive. Their children will not arrive either. Their grandchildren will not arrive. The people who eventually step onto whatever destination the ship was aimed toward will be the distant descendants of the people who launched, hundreds or thousands of generations removed from any individual who made the original decision to go. A civilization in a can, propagating itself across the void on a journey that no single human mind will experience from beginning to end. It is a compelling idea. It has been explored seriously in the scientific literature, not merely in fiction. And when you apply it to Andromeda, rather than to the comparatively trivial distances between stars, it fails, not for engineering reasons alone, but for reasons that reach into the deepest problems of what it means to sustain any organized human endeavor across time. At 10% of the speed of light, a velocity we have already established is beyond any technology within realistic reach. The transit time to Andromeda is 25 million years. That is the duration the generation ship must function without catastrophic failure. 25 million years. The entire history of Homo sapiens as a species is roughly 300,000 years. The entire history of the genus Homo, stretching back through every predecessor species in our direct lineage, covers perhaps 3 million years. A generation ship to Andromeda at 10% of the speed of light would need to sustain itself for a duration more than 8 times the total existence of anything that could be called a human. Every language spoken on Earth today has existed for a few thousand years at most. Every nation, every institution, every religion, every cultural tradition that has ever existed on this planet has collapsed or transformed beyond recognition in far less than 25 million years. The concept of a mission with a fixed destination and purpose, maintained across 1 million generations, has no precedent in any system of human organization that has ever existed. It does not have a mechanism. It is not a harder version of a problem we already know how to solve. The engineering problem is equally intractable, and it is useful to be precise about why. A closed ecosystem, a system that recycles all matter, generates sufficient food and atmosphere and water indefinitely, and maintains biological stability without external input, is not a solved problem. Research programs including NASA's Controlled Ecological Life Support System work and the Biosphere 2 experiment conducted in Arizona between 1991 and 1993 demonstrated just how difficult closing the loop actually is. Biosphere 2, built at significant expense to house 8 researchers in a sealed 3-acre structure with carefully designed ecosystems, experienced oxygen depletion, species extinctions within its habitats, and cascading system failures within a period of months. A system required to operate without catastrophic failure for 25 million years is not that experiment made more robust. It is a different order of problem entirely. No component of any engineered system, No material, no mechanism, no biological population has ever functioned without failure across anything approaching that timescale. Evolution itself, across 25 million years, would change the biology of the population aboard. The time dilation scenario does not dissolve these problems, it displaces them. A crew experiencing 28 subjective years at near light speed would step out of their vessel into a Milky Way that had aged 2.5 million years in their absence. The civilization that built the ship, wrote the mission protocols, maintained the communication relay and the political will to receive the crew's findings. All of that is gone. Utterly and completely gone. The crew would arrive carrying data about a destination observed from 2.5 million years in the past, equipped with knowledge of a home galaxy that no longer resembles the one they left, into a universe that has moved on by a duration roughly 8 times the entire preceding history of their species. The Andromeda they targeted would itself have changed substantially. Its massive blue stars, the brightest objects in its disk, live for only a few million years. They would be gone. New ones would have formed. The spiral arms would have rotated. The navigational framework built into the mission would be a map of somewhere that no longer existed in the form they were trained to find. The conclusion that the mathematics produces is uncomfortable, but not ambiguous. The Milky Way is not a launching pad for intergalactic travel. It is not a temporary address, a way station, a preliminary position from which some sufficiently advanced future civilization will eventually depart to explore the wider universe. The void between the Milky Way and Andromeda is not an engineering challenge. It is not a barrier awaiting a more powerful engine or a cleverer design. It is a constraint imposed jointly by the geometry of space, the speed of light, the energy requirements of acceleration, the biological limitations of every known form of life, and the thermodynamic reality of maintaining closed systems across geological timescales. The laws of physics permit you to know the distance. They do not permit you to cross it. Not with biology. Not within any framework of physics currently understood. The Milky Way is not a launching pad. It is the destination. It is the complete accessible universe for any organism that calls it home. And within its 100,000 light years of diameter, its 200 to 400 billion stars, its uncounted billions of worlds, there is more undiscovered territory, more unanswered questions, more possibility for contact and wonder and catastrophe and beauty than any civilization could exhaust in the remaining lifespan of the Sun. That is the confinement. It is also, properly understood, an extraordinary abundance. There is a question this video has been circling from the beginning without quite stating it. You have spent time moving outward, step by step, from the surface of a planet to the edge of the observable universe, and at each step, the previous scale has become invisible. You have learned that the nearest galaxy of any comparable size is permanently unreachable, that the universe beyond the local group is already, in a precise physical sense, receding beyond observation, that you are smaller, relative to what surrounds you, than any intuition about smallness can adequately represent. And yet, the Fermi paradox, named for the physicist Enrico Fermi, who raised it informally at a lunch table in Los Alamos in 1950, asks a question that the scale argument this video has been making cannot entirely answer. The Milky Way contains somewhere between 200 and 400 billion stars. A significant fraction of them are orbited by planets. Life emerged on at least one of those planets. The galaxy is approximately 10 billion years old. If even a tiny fraction of planetary systems produce technological civilizations, the galaxy has had an enormous amount of time for those civilizations to arise, expand, communicate, and make their presence known. And yet the sky is silent. No signal, no unambiguous artifact, no confirmed contact of any kind. One structural answer that follows naturally from everything this video has established is this. If the void between galaxies is physically foreclosed for biology, then even a civilization that had colonized every habitable world in the Milky Way could not reach Andromeda, could not reach any other galaxy. The universe's architecture confines technological life to its galaxy of origin as effectively as a wall. The silence beyond the local group may not indicate absence. It may indicate confinement, written into the laws of physics, not into any galaxy's particular history. The great filter for intergalactic contact may simply be the speed of light and the energy costs of crossing empty space. But the question that matters most is not whether anyone else is out there, confined to their own galaxy as we are confined to ours. It is something smaller and stranger than that. Look at what understanding this confinement required. The European Space Agency's Gaia mission, a spacecraft placed at the second Lagrange point of the Earth-Sun system, scanning the sky with extraordinary precision, has catalogued the positions, parallaxes, and proper motions of nearly 2 billion stars within the Milky Way. The mass of Andromeda, 2.5 million light-years away, has been calculated from the dynamics of its satellite galaxies and the orbits of objects at its periphery. The mass of both galaxies' central black holes has been derived from stellar orbits that required decades of observation to accumulate. The merger trajectory, the timing of first pericenter, the geometry of approach, the probability distribution of the solar system's eventual position within the merged structure, has been modeled through simulations tracking millions of individual particles. The structure of the observable universe across 46 billion light-years has been mapped from measurements taken on a single planet by instruments that have existed for a few decades. All of that was done from here, from one rocky world, by one species, with instruments assembled over the course of a few centuries of scientific practice. The species in question stood upright for the first time roughly 3 million years ago. It began using written language roughly 5,000 years ago. It first looked through a glass lens at the sky roughly 400 years ago. And in that 400 years, it measured the universe. Now consider what arrives tonight. If you go outside after dark and find the right patch of sky, the Andromeda galaxy is visible to the naked eye from a dark location, a faint smudge, slightly elongated, in the constellation Andromeda. It does not look like much. It looks, if anything, like a small imperfection in the sky, a slight brightening where the darkness should be uniform. What you are seeing is the accumulated light of approximately 1 trillion stars, arriving at your eye after traveling for 2.5 million years through intergalactic space. The photons reaching your retina departed that galaxy before any member of the genus Homo had yet evolved, before any human hand had shaped a tool, before any human voice had produced language, before the entire tenure of your species on this planet had even begun. They crossed the void between two galaxies, navigating the near-perfect vacuum of intergalactic space at 300,000 kilometers per second, and arrived, at this particular moment, at the surface of your eye. You cannot go there. You now understand exactly why. No technology you are likely to ever build can bridge that distance within any human-relevant timescale. The void is not a problem to be solved. It is a permanent feature of the universe you inhabit, underwritten by the same laws of physics that allow stars to burn and planets to form and eyes to see. And yet, the light arrives. The photons complete the journey that you cannot. The information crosses the distance that the matter cannot. You are receiving a signal from a galaxy 2.5 million light-years away, processed by 3 layers of retinal cells and interpreted by approximately 100 billion neurons, in an organ that weighs roughly 1.4 kilograms and runs on roughly 20 watts of power. The universe built a boundary, and then, in the same act of lawmaking, it built the instrument that could detect the boundary, measure its dimensions, calculate the timescales involved, and understand exactly why it cannot be crossed. You are not at the center of the universe. You are not its purpose, its culmination, or its primary feature. You are a temporary arrangement of ordinary matter on a small planet orbiting an unremarkable star in one of 2 trillion galaxies. And you are the part of the universe that looked up and worked out what it is. That is not a small thing to be.